Okay, guys, so now we're going to get to like the final idea within the energetics chapter, which is spontaneity. And so we're going to do a kind of tying some loose ends today. So, is a reaction spontaneous? Or does it require the input of energy? Now, we're going to expand on this later, but spontaneous simply means once you get it going, does it go to completion? It doesn't mean that it spontaneously happens like something spontaneously combusts into fire. That's not what we mean by spontaneous. What we mean is once it begins, does it complete, or do you have to continually add energy to it over and over and over again to make it continue reacting? That's the idea of spontaneity. And so let's backtrack for a second and let's look at enthalpy. And let's look at the idea of spontaneity with enthalpy. And so if we have our enthalpy level diagrams and we have an exothermic and an endothermic reaction, and so an exothermic reaction we'd have something that might look like this, and for an endothermic reaction it might look like this. And we talked about what is more stable, and the lower you are, the more stable. So this would be stable, and this would not be stable necessarily, relatively speaking. And this would be more stable, and this would be less stable. All right, so what would be favored? A stable situation or an unstable situation? Well, you ought to be able to figure out that a stable situation is more favored. And so this is more likely, if you will. It's more favored to be stable. And so an exothermic reaction, does that produce a favorable result? Yes, it does. That's a favorable result. So the likelihood of a reaction that experiences an enthalpy change that is negative of being spontaneous, that seems to favor that idea. That, hey, yeah, spontaneity would be moving towards stability. So you can even almost think of a rock sitting on top of a hill. Is it likely that once the rock begins to roll down the hill that it goes all the way down the hill? Sure. On the other hand, you could have a rock down here, and you could push it, and it might go up the hill, but it's going to come right back down unless you continually add energy to it to get it all the way up to the top of the hill. And once it's there, once you've added that energy, it could rest there. So this is an unfavorable situation as far as being spontaneous is concerned. It's not a rock is not going to spontaneously move up the hill. That's not going to happen. And so for enthalpy, exothermic tends to be favorable and endothermic tends to not be favorable. So exothermic would probably favor it being spontaneous, and endothermic would not favor it being spontaneous. Now, we need to expand our idea here, and we'll do that in a little bit. As far as you can have an exothermic reaction that's not spontaneous, and you can have an endothermic reaction that is spontaneous. So there's more to it than this. We're just talking and solely looking at enthalpy changes. What tends to be favored and not favored? So exothermic is favored, endothermic is not favored. Okay, so then you have the idea of entropy, and you can look at a similar kind of setup for entropy and say we have a reaction. So the reactants go to the products. And in this case, we had low entropy to begin with and high entropy to end with. And so the entropy change here was positive. And here the entropy change from reactants to products is negative. So which of these situations is favorable as far as entropy is concerned? Well, this is favorable. It's more likely to go in this direction. This is not favorable. The universe, remember we talked about this, the universe is moving towards randomness, towards high entropy. High entropy is the natural progression. More disorder is natural. It's not natural to become more ordered. And so You can't do the pushing the rock up a hill analogy here because it's wrong, but just keeping in mind that as you go up in entropy, that's more likely, that's more favorable. And so we have this idea of increasing entropy is favorable, and back here we have this idea of uh, exothermic or decreasing enthalpy is favorable. And so those are the two basic concepts that are going to play into the idea of spontaneity. Now, so you have these two things at work here, and we're going to combine them into a new concept. And that new concept is what is called Gibbs Free Energy. Gibbs Free Energy takes into account both the enthalpy and the entropy of a reaction and does the calculations to see if the reaction is spontaneous or not spontaneous. Okay? And the spontaneity, make sure you write this down or memorize it. The spontaneity of a reaction depends on the sign of Gibbs free energy. If you know the sign of Gibbs free energy, you know if a reaction is spontaneous or not spontaneous. So the symbol for Gibbs free energy is a capital G. Okay? And so let's look at the sign of Gibbs free energy. If you have Gibbs free energy, it can be negative, and Gibbs free energy can be positive. And so what determines spontaneity or not spontaneity? If the sign of Gibbs free energy is negative, then the reaction is spontaneous. If the sign of Gibbs free energy is positive, then the reaction is not spontaneous. Now, I want you to keep in mind, remember again, spontaneous in the sense of this chemical idea does not mean that it may just spontaneously happen, such as spontaneous combustion. It means that once the reaction begins, the reaction moves to completion without any additional input of energy. Whereas the idea of non-spontaneous means that if you want to keep the reaction moving forward, you must continually provide energy to it on a continual basis. As soon as you stop providing energy to it, the reaction will stop happening. And so that's the idea between spontaneous and not spontaneous. And so negative Gibbs free energy is spontaneous. Positive Gibbs free energy is not spontaneous. Okay? So there is your introduction to Gibbs free energy.